Here are two groups of labeled points on a plane, one class in blue, one in gold. And here is the question that runs this whole lesson. Suppose we want to squash all of this down onto a single line, from 2 dimensions to 1. Which direction should that line point so that afterwards the two classes stay as far apart as possible? Finding that best separating direction is exactly what linear discriminant analysis does. It uses the labels, so it is supervised, and it gives you both a classifier and a way to reduce dimensions. Let's actually do the squashing and watch what happens. Same two clouds on the left. On the right, I'll build the one-dimensional picture, the shadow each point casts on our chosen line. First, a bad choice. Project straight down onto the vertical. That keeps only each point's height. Watch the shadows land. Disaster. Blue and gold shadows sit right on top of each other. Both classes cover the same stretch of the line. Squashed this way, you could never tell them apart. Now the LDA direction. Here, straight across. Keep only how far right each point sits and project onto the horizontal. Beautiful. The blue shadows bunch on the left, the gold on the right, with a clear gap in between. Stack them into two histograms and you get to separate humps, cleanly split. That is the whole goal in one image. Find the direction that pushes the two class means far apart while keeping each class tight and the humps separate. Let's put symbols on it. Choosing a direction is choosing a unit vector W. Projecting a point X onto that line is just one dot product. Y equals W transpose X. Every point becomes a single number. Two quantities matter after projecting. The projected mean of class K is W transpose mu K, where each class lands on average. And the projected spread of class K is W transpose SKW, where SK is that class's own covariance matrix that measures how wide the hump is. So a good direction does two things at once. It makes the gap between M1 and M2 large, and it makes both spreads small. Push the means apart. Pull each class tight. To turn push apart and pull tight into one number, we build two matrices. The between class scatter comes from the mean difference. It captures how far the class centers sit. The within class scatter is simply the sum of the two class covariances. It captures the combined internal spread. Here is why those matrices are the right ones. Project them along W and the algebra is clean. The squared gap between projected means is W transpose SBW. The total projected spread is W transpose SWW. So we form their ratio. And this is Fisher's criterion. Big gap on top, small spread on the bottom. LDA chooses the W that makes this ratio as large as it possibly can. And for two classes, the maximizer has a gorgeous closed form. The best direction W is proportional to SW inverse times the mean difference. No search, no gradient descent. One matrix solve. Read it as a story. The mean difference points from one class toward the other, the raw separation. Then SW inverse tilts that arrow, deflating it along whatever axis the classes are noisy on. The proportional sign just says length doesn't matter, only the direction. Once you have the direction, classifying is easy. Project everything onto the line. The two class means land here. M1 on the left, M2 on the right. For equal priors, the threshold sits at the midpoint between them. Anything on the left side we call class 1. Anything on the right, class 2. That is the entire decision rule. Send a brand new point in, say it projects to here, past the midpoint. It falls on class 2's side, so class 2 it is. One fine print assumption sits underneath. LDA assumes the two classes share the same covariance shape and are roughly bell-shaped. Under that assumption, the boundary is a straight line. Let each class keep its own covariance instead. And the cousin method, quadratic discriminant analysis, QDA, bends the boundary into a curve. More flexible, but it needs more data to pin down. Let's grind one all the way through with real numbers. Two classes, 3 points each. Class 1 clusters on the left, Class 2 on the right. Step 1. The class means. Average the x values of Class 1, 1 plus 2 plus 1, over 3 is 4/3. The y values average to 2. Do the same for Class 2. X averages to 16/3, y again to 2. Step 2. The within class scatter. Each class has the same shape, tight in X, looser in Y. So their covariances match, and adding them gives SW, 2/3 on the X diagonal, 2 on the Y diagonal. Step 3. Subtract the means. The difference is -4, 0, pure horizontal, and invert SW. Because it's diagonal, you just flip each entry, 3 halves and 1 half. Now multiply. SW inverse times the mean difference gives -6, 0, which points along the x-axis. 1, 0. So LDA's verdict is project onto the horizontal, which is exactly right. The classes differ only in x, so the x-axis pulls them apart perfectly, and the y direction, pure noise, is thrown away. You might wonder, why not just use PCA to drop a dimension? Because PCA chases the direction of most variants and never looks at the labels. LDA chases the direction of most separation using them. They can point completely different ways. Let me show you exactly when. Here's the trap. 4 points class 1 low, class 2 high. The data spreads most along the diagonal, so PCA would pick that. But the two classes are separated vertically compared to candidate lines. The vertical U1 and the diagonal U2, the high variance one PCA loves. We'll score each with Fisher's ratio. Project onto the vertical. The class means land at 1 and 5, a gap squared of 16, over a spread of 2. Fisher's ratio is 8. Project onto the diagonal instead. The mean squash closer, gap squared of 8, over a larger spread of 4. The ratio is only 2. 8 beats 2. So LDA picks the vertical, even though PCA would have grabbed the diagonal for its bigger variance. Maximum variance is not maximum separation. That gap is the whole reason LDA exists. LDA is also a dimensionality reducer, and it scales past two classes beautifully. With more classes, that single best direction becomes a general eigenvalue problem. SBW equals lambda SWW. Each eigenvector is a discriminant direction, but there's a hard ceiling. The between class scatter is built from only C class means around one overall mean, so it has rank at most C-1. That caps the number of useful directions at C-1. Two classes give you one direction, a single line, exactly what we drew. Three classes give at most two, enough for a flat two-dimensional plot. That makes LDA a favorite for squeezing many labeled classes down into a picture you can actually see. Your turn. Class A's mean projects to 2 on the line. Class B's mean projects to 6. A new point lands at 5. Which class does LDA assign it to? Pause and work out the threshold first. Here's the reasoning. With equal priors, the threshold is the midpoint of 2 and 6, which is 4. Our point sits at 5. That's past 4, on class B's side, and closer to 6 than 2, 2. So the answer is class B. If you found the midpoint, checked which side, and landed on B, you've got the entire decision rule in your hands. Trap 1. The big one. LDA is not PCA. PCA is unsupervised and maximizes variance. LDA is supervised and maximizes separation. Never swap them. Trap 2. LDA cannot run without labels. Every piece, the means, the scatter matrices, is built from which class each point belongs to. Trap 3. Don't forget the shared covariance assumption. If the classes have genuinely different spreads, the honest boundary is curved, and QDA is the right tool. Trap 4. Don't expect more than C-1 directions. 3 classes give you 2, never 3, however much you'd like a third. And trap 5. A reassuring one. Don't fret over dividing by n or n-1. It rescales SW, but the direction of SW inverse times the mean difference is untouched. Let's lock it in. LDA projects every point onto one line. Y equals W transpose X, turning a cloud into a single number. It chooses that line to maximize Fisher's ratio, the gap between class means over the spread within each class. Separation on top, noise on the bottom. And for two classes, the winner is closed form. W proportional to SW inverse times the mean difference. Supervised, label aware, and a linear boundary. Remember those three lines, and discriminant analysis is yours.